Hello physics students. In this video, I'm going to talk about dielectrics. But before I do that, I want to point out something that I didn't point out back when we first studied parallel plate capacitors. So remember, I put this formula up the first day, we talked about capacitors, and then we eventually derived that this is the capacitance of a parallel plate capacitor. C, the epsilon zero constant that we've been using, the variable A, which is the area of just one of the plates in the parallel plate capacitor, divided by the distance, how far apart those plates are. But imagine we decide to construct a parallel plate capacitor, and we're going to make a big one because we want to make the capacitance as large as possible. So imagine I make a capacitor that's 1 meter by 1 meter. That's the size of one of the plates. So I put in epsilon zero, and here I'm just looking like an order of magnitude estimate of the capacitance of such a capacitor. So I'm not worried about the 8.85. Let's just say epsilon zero is 10 to the minus 12, just to give us the idea of the approximate magnitude of such a capacitor of a 1 meter plate size. And then I put in the distance of how far apart I'm going to put my two plates. Let's suppose I put them a millimeter apart, pretty close. If I make such a capacitor, I get a capacitance that's of the order of magnitude of 10 to the minus 9th farads. In other words, a billionth of a farad. Okay? So 1 by 1 meter, imagine a capacitor, a metal plate that's like this by this tall. This would take up my entire back seat of a car, maybe, most of it. A giant capacitor like that, carrying it like this, big metal sheets, and it's a billionth of a farad. If I want more, maybe I need even bigger, right? And yet, we had in class, I showed you, a capacitor like this, which is 0.006 farads. In other words, 10 to the minus 3, not 10 to the minus 9th. And it's much smaller than the giant 1 meter capacitors. And then 0.006, and then we saw 1 farad. So like 1,000 times more than this one. And it's smaller. And then there's another 1 farad capacitor, even smaller. And then a 10 farad capacitor. So how is it that they're making capacitances so large? 10 farads is an enormous capacitance. When we need giant capacitors to get more capacitance, obviously there's some kind of other technology at play. The geometry and the shapes of the metals is one. So they get better about shaping the plates, not necessarily parallel plates, but other kinds. The other piece of the puzzle is they put materials between the plates. It's not a vacuum. They put materials that up the capacitance. Those materials are called dielectrics. So the first thing that I'm going to do is explain what a dielectric does, or I should say any matter does, any atoms or molecules in the presence of an electric field. Up until now, we've been just studying the electric field caused by something with a vacuum surrounding it. We never thought about, well, what about if you put charge into something like a ball of wax or something like that, where there's atoms and molecules around it. So, topic for today, dielectrics. I have two diagrams here, polar molecules, analyzing what happens to polar molecules in an electric field and nonpolar molecules. Remember in chemistry class, a polar molecule is basically, it's not an atom, but it's a combination of atoms, and one side of it is positive and the other side of it tends to be negative. So the charge isn't evenly spread out. We say it's a polar molecule. So if we have no electric field, the positive-negative orientation is just random. That's what I'm trying to show here. Sometimes the positive of this one's down, then the positive's up. Sometimes it's right, sometimes it's left of the various molecules. If I put a field in, or put those particles in a field, those molecules, maybe I put it in a parallel plate capacitor. creates an electric field. What that's going to do, it's going to create a torque, a twisting force on each of these particles, because any positive is going to want to shift to the right and any negative to the left. So look at this. This molecule is going to be pulled like this, or this part of the molecule pulled this like this, and this one's going to go the opposite direction of the field. So this is going to swivel around and maybe align like that. The alignment isn't perfect, but it's sort of more or less aligned where all the positives are to the right and all the negatives are to the left. What that does is it creates, the molecules create their own electric field pointing from plus to minus. And so the molecules within the molecule make an electric field like to the left, thereby slightly canceling the external electric field. So the net electric field is reduced by a certain amount. So that's what happens with polar molecules present. What about if you had nonpolar molecules? Remember, those are molecules where you have the nucleus of the atom and then the electron cloud is evenly spread out. So when you're outside, there's no electrical effects because even if think about our Gauss's law, you got a positive and then an equal negative, you make a Gaussian sphere, Q enclosed is 0, everything's symmetric, E is 0 all around it. So maybe that doesn't have a dielectric effect. It actually does, because here's our nonpolar molecules with no field, even spread of the charge. But what will happen is, when you put an electric field pointing to the right, the nuclei of the atoms are pulled to the right. They go in the same direction electric field. While the electron cloud is now pulled to the left, so the atom kind of stretches out and becomes polar. It wasn't before, but the electric field made it polar, which makes an electric field going that way, thereby reducing some of the electric field. So whether the molecules are polar or nonpolar, the net effect is that atoms or molecules make E get smaller. Okay, so let me create a pause in case you're not caught up with this, you can catch up. Okay, so how do we then figure out what the new electric field is? So this method is for what we call linear, isotropic, homogeneous dielectrics, sometimes abbreviated LIH, more than you need to know, but let me just put it here for a little background. What do we mean by linear? It means that the effect is proportional to the electric field, the effect of reducing. So it's not like a parabola where, you know, it sort of reduces a little bit and then all of a sudden it really reduces it once the electric field gets to a certain threshold. No, it's a linear reduction. Isotropic means that the electric field effects are the same in all dimensions, whether you go whatever direction. And homogeneous means that if you've got a block of this material, the effects of the dielectric aren't more or less in any one region. They have the same effect everywhere on the electric field throughout. So what that does is it, as we say, reduce the electric field. The way you can calculate the new electric field is well, remember we had two techniques primarily. We had the electric field around a point charge, E equals kq over r squared, Coulomb's law for electric field. And so you can use that formula, and sometimes we use that through integration for charge spread over like a stick or an arc. So kq over r squared, you can modify that by putting a little symbol here in front of the epsilon 0. It looks like a K, but it's a Greek letter. If you want to sound like a boorish, unsophisticated person in a physics society, you could come in and say, hey, they put a K in front of the epsilon 0. Everyone sort of chuckles, right? Oh, this guy calling it a K. No, it's a kappa, right? You got to sound with the lingo sophisticated. You know it's a Greek letter. Kappa in front of the epsilon 0. And so that's all you do with the kq over r squared. You can use that formula, but you just have to put this new factor. I'll talk more about it in a minute. Or if you want to use Gauss's law, instead of, oops, mistake, ds. Okay. EDA equals Q closed over epsilon 0, put a kappa in front of the epsilon 0. That's as difficult as it gets. You put a constant in front of epsilon 0 wherever it appears, and you have the method for finding the new electric field. But what is this kappa term? So it's called the dielectric constant in addition to being called kappa. It's a number that's always greater than 1, and it's unitless. So like, for example, if kappa's 2, That means the dielectric makes the electric field a half of what it was without any substance there in a vacuum. If it's Kappa's 3, then you have a certain electric field in a vacuum, surround it with a material, and now you have 1/3 of the electric field. That's all, okay? Now, before I show you the table on page 732, I just want to note that when you put atoms there, now you have the problem where the atoms can break apart because of the electric field and ionize. So now, putting the dielectric around a charge, you limit the amount of electric field possible. Because if there's too much electric field, the atoms break apart, zap, and the charge gets lost and the dielectric gets burned up or whatever, ionized. Okay, so that's it's a price to pay of using a dielectric. All right, so if you need a moment, I'll create a pause to allow you to catch up and copy this down. Okay, so the table on page 732, so let me just hold up our textbook here. And you can see that for air, the dielectric constant is approximately 1.0, which means air doesn't really affect the electric field by much. It's slightly more than 1, so air reduces the electric field by a little bit. And also you see this dielectric strength. So this tells you the electric field, the maximum before we get a spark. So I talked about that in the Van de Graaff generator video. But you've got a whole bunch of materials here. And you see various dielectrics. So like, for example, Pyrex is a type of glass, 4.7. So everywhere there's epsilon 0, you put a 4.7 in front of it for Pyrex glass. And a whole bunch of them. And then you see strontium titanate was one of the biggest dielectrics here, 310. Really reduces the electric field. And also, you know, the limits here of the electric field. Many of them in the book aren't here, as I mentioned in the Van de Graaff generator video. So this table, if you need the dielectric or to figure out how much electric field is limited now because of those new atoms in the way around it. All right, so now that's what a dielectric does. That's what it does to electric field. Now we're going to look into how it affects the capacitance, right? How do I get this tiny thing to be 10 farads, okay? Enormous. By the way, let me see, I'll bring this close to maybe you could see it. I don't know how good the focus will be. You see how it says 10 farad on it? And then also it says 2.5 volts. Because we have such a strong dielectric, now we can't put this capacitor beyond 2.5 volts without causing a spark in the dielectric, ruining the capacitor. So again, the electric field now, the price of that is you can't put as much voltage because it'll make a spark in the capacitor and ruin it. All right, so how does this affect capacitance? Obviously, it's going to make it go up, right? That's what I've been saying by showing you those examples. So let's see how we could reason that out. So oh, I forgot to put isolated. Well, I guess I'll do it here. So remember what I mean isolated? I got two parallel plates. I charge them up with maybe a battery, and then I disconnect the battery so the plates are now not able to lose their charge. They're like sitting there. So this is before. What I have is I have plus Q0, negative Q0, and then after, I've got this is still positive up here, this is still negative, but I've got this block of material. Maybe it's wax, maybe it's strontium titanate, maybe it's Pyrex glass. I don't know. I put something in here. And it's got a dielectric constant kappa, 4, 1.5, 310, right? Whatever. Okay, so how is the charge affected when I put this in here? So the first thing we can say is that the new charge is exactly equal to the old charge. And why? We said this was isolated. That means charge is conserved. Just because I put a slab in here of glass, well, where is the charge going to go? Nowhere. It's stuck there because of the fact it's isolated. So now we also know that the electric field is E0 over kappa. It's been reduced. And that comes from over here, right? Over here. You could see that 1 over 4 pi epsilon 0, I put a 1 over kappa there, so we have less electric field by a factor of kappa. So what that's going to do is it's going to reduce the voltage also. Why? Remember, V equals ED. And so we have the same distance here, but with less electric field, with the same distance, we're going to have less voltage. Okay? So now, here's how we can reason out that C equals kappa times C0, because C equals Q over V. So if we have the same charge as before, but we've got less volts, we're going to have more capacitance. Okay? So it'll be more efficient at storing charge for the given voltage. And finally, one other point, the electrical energy. Well, the electrical energy is the old electrical energy over kappa. How can I reason this out? Well, remember, one of the capacitor formulas for energy is 1/2 QV. So if we have the same charge, but we have less voltage now, we're going to have less energy in the capacitor. Now the question is, energy is conserved, it cannot be created or destroyed, it has to go somewhere. Where did this energy go? Okay. Again, just like when I put the metal plate in a few videos ago, the capacitors, the dielectric is going to be drawn in and it's going to accelerate and gain kinetic energy. So if I hold it back to prevent it from shooting in, this is going to do work on me. And therefore, I got the work while I slowly put it in. Or we could just say the capacitor did work on dielectric, pulling it in. All right, if you need a little time to catch up, I'll create a pause here. Okay, now we're going to do the same analysis and see if we get the same conclusion if the capacitor remains connected to a battery at all times while this dielectric is inserted. So before, maybe I'll remember, this is how we draw battery. And now we're going to insert that dielectric while we maintain the battery connection. So let's say after This is still going to be positive. This is going to be negative. But now we've got a dielectric in here. Oops, I accidentally made these plates further apart. They're supposed to be the same distance apart. All I'm doing is inserting this dielectric with a constant kappa. Okay, so the next thing, this time, we don't know if the charge is the same. So let's skip over that for a moment. One thing we do know, though, is that the voltage is the same. Okay. How do I know that? Well, the battery, right? The battery maintains that voltage to chemical reactions. So it stays the same. That means, here's something a little counterintuitive. People say, I put a dielectric, it makes the electric field go down. Not in this case. If the voltage is the same, the electric field has to be the same. I thought the dielectric reduced the electric field. Well, remember, the voltage for a constant electric field is ED. If I have the same voltage because of the battery, the same distance because I haven't altered the plate separation, then same has to be the same. How could that be? I thought the dielectric reduced it. Well, what has to happen then is the charge had to increase by a factor of kappa. Okay. Now, how can I reason that out? Well, remember that E equals sigma over epsilon 0 for a capacitor with a vacuum in between. But if I put a kappa over here, because of the dielectric, in order for the electric field to stay the same because the battery holds it the same, if I put a kappa here, I got to put a kappa up there. The charge density on the plates is more. The battery packed in more charge. That's what kept the electric field constant. Okay? So, the next thing, how about the electrical? We could look now at the capacitance. What happens to the capacitor? I guess I have room here, but I want to be consistent with over there. Well, if I have more charge for the same volts, once again, I come to the same conclusion that the capacitance goes up. I get more capacitance by putting materials in between the metals. Okay, that's how I can get it higher. So again, this comes from C equals Q over V. So if I have more charge, same volts, more capacitance. And then finally, the electrical energy. That also, now this time, the electrical energy increased. How do I reason that out? Well, if I have 1/2 QV, more charge with the same volts, I'm running out of room here. Hopefully you could see this. 1/2 QV, the energy in the capacitor equation, so that's how we can reason out there's more energy. Now, energy cannot be created or destroyed. Energy has to come from somewhere. Suddenly this whole arrangement has more energy than before. Where did it come from? The battery. By pumping more charge into the capacitor, we're also pumping more energy. So the extra energy came from the battery. Okay, so if you need a moment to catch up, I'll create a pause to allow you to copy this down. One last thing. So remember, I was saying that the atoms here are going to shift and become like polar like this. And they're all, so you see that there's minus charge that ends up accumulated on this plate. And the atoms here are tilted like this. And so there's positive over here next to the negative plate. What that does is along this top surface, there's a sigma, a certain charge density, negative, and there's a certain charge density, positive, along the surfaces of the dielectric material. We can actually calculate those. How? So, calculating sigma dielectric Okay, so how can we go about this? So here's our capacitor. Let's now not call it charge Q, we'll call it sigma 0. The charge density on the capacitor plates So I put an equal number. It looks a little misleading here. Let me move these sigmas. Okay, maybe it looks a little clearer there. So now I put the dielectric in there. And as I just said, the top of this will become slightly negative, and the bottom here slightly positive. And so this has a plus sigma dielectric, negative sigma dielectric. And I can apply Gauss's law to find the electric field inside here. So the Gaussian surface I'm going to choose to create looks like this. Okay, so Gauss's law for this surface because of the dielectric is kappa epsilon 0. Now, the only surface through which there's flux here is the bottom surface. Electric field outside of a capacitor, 0, as we learned. So this left side just becomes E times the area down here. So I can write that as E area equals the Q enclosed, which is sigma 0 area over kappa epsilon 0. That's the way I can find the electric field using the method I talked about by inserting a kappa. But another way I could think about this is to say that the Q enclosed is actually the Q caused by the metal plate here, and that Q would be sigma times area. So that would be sigma 0 area right here. And then I'm also enclosing the negative charge from the dielectric. So here I could write minus sigma dielectric times the area. That's the charge that's in there because of the dielectric. And here on this side, what I'm going to do is I'm just going to put epsilon 0, because what I've done is by including this, I've factored in the dielectric. So without including that charge, I need this to factor in the dielectric. or I could get rid of the dielectric and factor in the dielectric by realizing that it reduces the charge. So this is like the factor of sigma in the bottom. So just looking at these two sides, you could see that area goes away and so does the epsilon zero. So what I have is on this side, sigma 0 over kappa equals sigma 0 minus sigma dielectric. Oops, I guess I was still thinking of a fraction. And so if I move sigma dielectric to the other side, move this term to this side, I get an expression for the charge density on the surface of the dielectric will be sigma 0 minus this. So if I, because I'm running, well, you know what, maybe rather than be lazy and risk confusion, let's do it right. Okay, so sigma dielectric equals, what was it? Move that to the other side, and I got sigma 0 minus sigma 0 over kappa. If I take sigma 0 out, I have the expression like this. So the charge density on the surface of the dielectric is less than the charge density on the plate in the capacitor. So maybe like a half or a third, but some portion of it, because this is going to be less than 1. And it depends on the kappa. So there's how you could calculate the charge density on the top of a dielectric. All right, if you need a moment, I'll create a pause so you can copy this down. Okay, so in conclusion, the dielectric, any atoms or molecules reduce the electric field in a material unless the battery maintains it and keeps it constant and it compensates by charge. But in general, all things being equal, it reduces the electric field. That reduces the voltage in a capacitor. Reducing the voltage in C equals Q over V increases the capacitance. The new capacitance is just the dielectric times the old capacitance. Nice and easy. Just multiply and it's an increasing effect. So that's how we achieve one of the ways those big capacitances with our capacitors. Okay, so I hope you enjoyed our physics video, dielectrics. We are now done with conductors and capacitors. I'll see you in the next physics video, which is the next topic.